how is that related to doing game? So let me go back to the. So in fact, in robots, what we do is that we study how to make a robot, right, to work, which is an artificial thing, to be smart in the environment, right? We want him to do things. And then it turns out, obviously, we work on real robot. Some of you may recognize this robot, the Honda robot. But also we do a lot of simulation. We actually, it's very expensive to buy a robot and work on it. It is not, millions of dollars, right? So we're not gonna have a robot, for each of us. So we do, we do simulate robot. And in a lot of the things that we do motion planning, right? We plan the robot, how they move and how should they move. It's all about robots' capability to reason about space. And then back, so I started the first company, a company that focused on game, because we realized that, a game character, right? So I don't know how many of you actually recognize what this game is. It's probably older than you. So this is, you probably heard of Prince of Persia, which is a classic. But Prince of Persia is actually the first game that got into 3D after, it, did the Quake. And also one of the games that I worked on, right? We provided the character engine for this game. So if you look at it, the game characters are just a little bit better looking simulation of robot, right? They look better, right? And they obviously have the weapons and stuff, but they really need to have the same intelligence. If we want a game to be realistic, to be fun, the game characters should have the same level of intelligence as a robot should in the physical space, right? So that's really kind of the intuition, behind me and then a group of Stanford students went into doing, taking the robotic technology and using game. In fact, you actually see many games involving robots, obviously, right? So that's kind of why we, how I got into the game business from a, research, and I got my PhD in robots, was that we realized that the AI that we created for the robot can be very useful for the simulated robot, which is, could be a character, a humanoid character in the game space. So I started that back in the mid-90s when the first PlayStation was launched, and I spent about 20 years in the game industry, mostly providing AI for games. So who knows who actually invented video game? Anyone knows who invented video games? Let me see. Or when was video game invented? So yeah, someone, if you know who invented, just speak up. No? So believe it or not, video game was invented by a nuclear physicist. So, you say, well, why would nuclear physicists invent a game, right? So his name is William Higginbotham, right? So I don't know whether I misspelled his name. So he's a nuclear physicist that works in Brooklyn National Laboratory. So there is a laboratory, national laboratory that focused on, making nuclear bombs and all kinds of research with nuclear physicists. So the reason why he did a game is that the game is called the two-player tennis. So it looks like this. It runs on doesn't really look too much like a computer. This is called analog computer. Remember, this is back in '58. Right? So this, the digital computer is not even invented. It runs on a little, almost looks like a little instrument, right? And this instrument was obviously originally intended for doing nuclear, research, right? Making nuclear bombs and other things. The reason why I did that was that, there's an open house for high school students to come and visit them. And every year it was a very, very boring event. So you want to have to do something fun the kid can interact with. And so decided to make a game. And why do you think that he make so this is, he make a game is tennis for two. So how many of you actually know why, obviously, why does he make a tennis game? Not something else, right? Obviously one thing is the tennis, basically just a ball going back and forth with a net in the middle, like you can see. At the time, the computer, the monitor, very rudimentary. But more importantly, this device, the analog computer, had the capability to calculate missiles traveling in air with air resistance, which is very similar to a tennis ball getting hit, right? Obviously, a tennis ball goes a lot slower than a missile, but it's the same physics. So since they already can calculate a ball traveling with the air resistance, you can actually do quite a realistic tennis simulation. So he made this, it was a big success. So that's how game was invented. So by a nuclear physicist in a national lab. And this actually laid the foundation for the first commercial, there's probably argument, but this is the very first commercial game called Pong, which many of you probably know of, right, heard of, in '92 by Atari. So it's an arcade game. Again, very similar to this tennis. There's two pedals, right? This little two pedals, the white dot, and the ball going back and forth with the white net. Is an arcade. It's a big success. And Pong is really the first game to launch a huge industry, right? So, back in '92. Can you guys guess how many people play games in the world today? How many, obviously you guys play games, most of you. How many people you think play video game today in the world?
1 billion.
1 billion. Another guess?
More than the last one.
More than 1 billion.
More than 1 billion. Okay, that's a good guess.
The people in the world.
4 billion. Well, so today, 2.7 billion people. So obviously, I don't want to use as an excuse to tell your parents that you say I should play a game. Look, there's 2.7 billion people playing game. Obviously, they're playing all kinds of games. And I assume, I hope they're not playing 4 or 5 hours a game. But there's also a huge industry, right? It's projected to be a $200 billion industry. So huge industry, and all started by a little ping pong ball going back and forth on this screen. So obviously, so this is actually, it's about the same time, '92. The first game console was launched into your house, right? So you look at it, look at this old TV, right? The console connected to TV, and this, the palm, right? So this is the white dots are the pedals, controlled by a little controller, and the white square here, the ball. Why do you think the ball is square? I mean, shouldn't ping pong ball be round?
Because the graphics weren't good back then.
Yeah, so the graphic, at the time, right? So the resolution, I will talk a little bit about that pixels, right? So there are not many pixels on the TV. So the pixels are quite large. So obviously you don't want to make a ball that's half the size of the screen, right? So then they can probably use 4 pixels to make the ball, right? So square. Now, obviously, we fast forward. You guys probably all know and maybe have one of the new the console, right? PlayStation 5. So look at the graphic, right? The graphic is now approaching film, right? So cinematography, they're real-time lighting. So there's obviously the reflection. If you guys know graphics, what they call sub-level scattering, like that kind of make the skin look natural. If you can look at some of the latest game, right, sports games, the skin looks very natural. So they're not only reflecting on the surface, they actually have the light scattering subsurface. So, you can see the difference, right? It started out many years ago as a 4 pixels square. Now, that's what it looks like. So obviously, the game industry has gone far, for the last, 92, 40, 50 years. So not many years, given the progress. But underlying this is tremendous research, tremendous work, right? So, so that's, we're going to touch a little bit of that. So, I wanted to, so like I said, the first thing we want to know is what are games? So let's just kind of review some of the games that classic, right? So in fact, if you look at all the games, they change the graphic, they change the theme, but the game, at the basic level, they're very, very similar. So what is this game?
Space Invaders.
Yep. What is this game?
Mario
All-Stars?
Yeah, so one of Mario's game, Super Mario. You guys all know this game, right?
Pac-Man.
And what about this game? Donkey Kong.
Donkey
So these are all started out in arcade, and then all handheld, right? At the time, the TV, obviously there's a TV game with the metal box, but the where the TV game, but the very popular arcade games, right? People actually go to arcade because not many people has buying a game console quite expensive. So, but for a long time, the handheld, the little, Nintendo make those handhelds and Sega, and those handhelds are very popular.
Wait, like the Game Boy?
Yeah, Game Boys. Yeah, so Game Boy has been one of the most popular generation. But if you look at it, so we look at this game, right? So this is a shooter, right? This is kind of how the shooter started. This is called side scroller, right? So kind of runners, right? This is a platformer, so you jump, jump, jump. And this in Pac-Man is somewhat unique. It's a game that's actually initially designed to attract non-game player, like female players. So in fact, a lot of so if you look at the other game, a lot of boys play them as shooters, and you don't really see many girls play Space Invader, but a lot of just like Candy Crush, a lot of women or girls play Pac-Man. So those are classics, and we'll look into those, and then the more modern ones. So you guys probably all familiar with this one, right? You know this game?
Fortnite.
Yep. So this is one of the FIFA sports game. This is
GTA.
Need for Speed, right? Racing, and then Sim, right? So I show you different things because I want to go back to the next slides. Like there are different type of games, right? Obviously, some of you guys, most of you, a lot of you may like to play shooters, but a lot of people like to play sports games, and also sim games of type. So there's different genres games, and they are all very similar. It doesn't really matter what the graphic look like. The genres are, transcend the story and transcends the graphic. It's really what we call the gameplay mechanics, right? In it. So there's a bunch of action, there's action game, right? From shooter, first person, third person shooter, platformers, the fighting games like Virtua Fighters, side scroller, but rhythm games. What I consider. I don't know whether you guys remember Guitar Hero, right? So that's, or you guys play Guitar Hero. So that's an actual action game. Not a shooter, but it's an action game. And another type of really popular game is a role-playing game. So from the really old MUD, do you know guys who know what MUDs are? What MUD stands for? So it's a dungeon game, right? So it's text-based, so role-playing game. And then obviously there's the action RPG, right? And then obviously the very popular one, the MMORPG, massive online, right? Multiplayer online game. So World of Warcraft is one of the obviously the well-known ones. And then you have simulation games, many simulation games. So we'll talk about that. In fact, SimCity, right? SimCity is a simulation game, and a very popular simulation game, Minecraft, right? So basically, you build a lot of building games. Are simulation games. And then finally, there's a bunch of sports games. It's not as popular as shooters or action games, but a lot of people like tennis and golf and football and soccer and FIFA and so on. And also racing, some we'll put racing in there here as well. So those are different game genres that, again, so the graphic looks very different, right? So compared to this one. But if you look at it, right, so it's, the gameplay mechanic is very similar. And the component make up those games are very similar. So let's now talk a little bit about, now we know, we know what, so what exactly are games, right? You guys play games. Have you guys ever thought about, what makes something a game? Right? Do you have you, like think, what makes something, so not even a video game. Let's think about what makes something a game, like a physical game, like a game that we play, not on video, right? So games are just structured play, right? You play, but game, so let you play, you play with your brother or sister at home, right? But sometimes you call it play, but sometimes you call it a game. What's the difference? So games are under some structures, but also games has element that makes it a game. So there's really 4 critical elements that makes something a game. So obviously I have some picture here showing the different type of, not video game, but game that you play, right? So, chess. This is, rock climbing, or you can be in a gym, you can actually go outside and climb. soccer, right? You play soccer, and puzzle, right? And so those are different games that people normally play at home, not video game. So we want to understand game first, and then we'll move to understand what video games are. So the element that makes something a game. So it has to have a world, right? A game world. Like what do you do? Right? Where do we do the stuff? But normally it's a simplified world, right? So not the whole thing, not the whole universe, right? Something simplified. For example, in a chess, the world is a chessboard plus the chess pieces, right? But more importantly, the world is governed by some natural or artificial rules. So in the chess game, mostly artificial rules, right? How the different chess pieces move. Well, in a rock climbing thing, well, you're going to be governed by the natural rule as well. You're going to fall down if you don't, if you can't hold up yourself, right? You just fall down by the natural rule or laws of gravity, right? Same thing in soccer. Well, you both have natural rules or laws, right? The physical part, as well as the artificial one, right? How you should play. What are the rules of the soccer game? And then, puzzles, again, so, the environment is the puzzle board, right? And then obviously the rules that you need to put all the pieces together. So it has to have a game world, the first thing, that governed by rules. Second thing, a way for the player to interact with the world, right? So in the chess game, well, you as a player, you pick up the chess piece and move it, right? And move it, right? Obviously climbing, you need to climb, right? So the way to interact with the game world. The third, it must have a goal objectives. It must have goals and objectives. So, obviously in chess, what the goal is that you want to win, right? You want to checkmate. In climbing, obviously you probably want to climb to the top. If there's, by some definition, if there's no goal objective, then it's not a game. It's just a toy. You play with it, right? You can still play with it, but it's not a game because you're not trying to achieve something. And the final piece, what makes a game is challenges. So the challenges in a game or opponents, right? So it comes in the form of obstacles, right? So for example, if you rock climbing, it's the environmental obstacles, right? It could be enemies, like your opponents, right? In the chess, your opponents, your soccer team, your opponents. Or it could be, enemy also opponents. If in a play, you don't really have obstacles, then some people call them puzzles, right? So for example, puzzle are also some puzzle considered puzzle games, right? That's what they call it. But for some people, consider puzzle not a game because there's no opponent. You're not fighting against somebody, right? So that's what really makes something a game, is this 4 key elements. So now, say what are computer games, right? What are computer games? So this is all different. I'm just giving you, so you probably get familiar with this middle one. Anybody know what the first one is for? The first game?
Final Fantasy.
Yeah, Final Fantasy was the last one. It's kind of the tomb. It's like a runner, one of those runner, right? Temple Run. I don't know whether you guys are. So Temple Run was actually when the cell phone first came out, one of the most popular games. It has like 300 million downloads or something like that crazy. So this is now. So if you look at this, it actually, what a computer game is just simulation of a real game, right? But without the physical limitation. You don't really have to simulate exactly what the world can. In fact, you can fantasize, right? You can have character that, carrying huge weapons, right? Or in this case, obviously, this Tetris, you have things fall down, they can annihilate. Well, obviously, it doesn't, it blows up, right? Obviously, it doesn't do that in the physical world. And in Temple Run, obviously, you run and all these things, and it runs, beyond the physical limit, how fast people can run, right? And how high can jump. So computer games are just simulation of games that we, before the computer is invented. So again, so it has all the elements that a game must have, right? You have to have a game world, right? So Tetris, this is game world. This is the game environment, right? So Final Fantasy, a little bit more complicated. There must be a way for player to interact, right? So, we'll go into that. How does a player interact? It must have challenges, right? And in the form of enemies or in the form of obstacles. And finally, games has objective. Temple Run, you have to run the fastest. This one, obviously, you need to see how long, what the score you get, right, and so on. But then there's one, so beyond this, since this is a simulation, right? So the first big difference is that it's a simulation, it's a simulated world, right? But since you simulate it, then you must have a way to visualize it, a way to see it, right? Otherwise, if you cannot see it, then you can't really play the game. So this is where, what we call computer graphics, a very important part of it in computer game versus the normal game. So now let's think about how do we now make games then, right? So, you know what a game is now. How do you make a video game? So, but basically, we want to see what are the building blocks for a video game, right? So that's really the key questions. So we already know what the games are. So that, it's kind of, and now, related that, right? So first we need to be able to simulate, right? We need to make a simulation, right? Because that's what the game was. And second, we need to have computer graphics, right? We need to somehow show the world, right? So this, this is the Donkey Kong. So this is simulation, right? The simulation, obviously, where all the the environment is, right? The world, and then obviously all the objects in there, and then you need to show it. User interaction. So how the players should be able to control the character, right? Game AI, the enemies, right? So in this case, the Donkey Kong plus all this enemy object, that little fireball. So actually for Donkey Kong, different level, they have different enemies. The game AI. And then you have a way, need to somehow have score, right? Keeping the score, how you score it. UI, which are common, right? So the display the score, some of the menu buttons and so on. And finally, you have music and sound effect. And there might be other minor things. But the key thing in a game, the key elements, right? Not the other one, not so important. The key element that without which you cannot have a game are the first 3 or 4 things, right? So let's just take a little time to look at each of this to understand a little better. What do I mean by simulations and graphics? So how do you simulate, right? How do you simulate a game world? And what does that mean from a computer science perspective, right? So you really need to do 2 things, right? So let's say look at an example of Candy Crush, and then this Donkey Kong. So you need to figure out a way to capture at any time the state of the game world. So in this case, what is a state? What describes this world? Obviously, it's all the grid, right? So this, you can describe this world as a grid, right? And then each grid has a candy, and the candy has a color, right? And in this case, the state of the worlds are where the enemies are, right? And where you are, right? And then obviously where the princess and when the Donkey Kong is, and also the road that you can go and the ladders and so on. So that's the state of the world. So basically, you need to know what all the objects are: the player, the enemy, the environment objects. And then they usually have properties, right? So, for example, some of the candy may have special property where if you string them together, they will have special effects, right? Obviously, for some of the enemy, they have speed that they travel on it, right? Or they can go down the ladder, or some of them cannot go down. So the object and the properties. And the second thing, in order to do the simulation of the world, is that you need to know how the state changes, right? You remember that the world are governed by rules, right? So the rules that govern the world, and under those government of the rules, how the state changes over time, which are actually come from 2 things. The thing evolves itself, right? So for example, with the enemies and so on, right? So, it goes around, and there might be other things, right? So if you're firing a bullet, the bullet will just go, right? Or you're falling, they'll fall down. So the environment will evolve by itself. But also the other thing is changed by the player action. For example, in this Candy Crush, your action is to switch the 2 candy, right? So your action will change the state of the world. So this is what we mean by, again, this is a very high level, given that we only have 1 hour. So very high level, what do you mean by simulating world? And as you can see that, there's a lot of element in here that, involving, so in fact, if you look at this, if you have learned programming, right, you would say, okay, those are variables, a list, right, that you need to do. And here's, you actually need to figure out a way to change those variables, right, as they will involve. Okay, So the second component, right, now you simulate the world, right? So something going on, but it's useless to the player if you cannot see it, right? You cannot see it. So you need graphics. So graphic is really a way to display the world, right, through a screen, right, a TV or computer monitor, or on the phone screen or handheld screen, right? That at any instant, but obviously you need to update frequently so that it looks like it's actually, like a movie, right, or happening in real time. So normally, for you will update at least 30 frames a second for it to be smooth, right? Or for some of the action games, you probably do it at 60 frames a second. That's why some of you guys who do shooter, you buy more and more expensive computers so you can run faster, right? A better frame rate. So it's really graphics. It's just a way to describe the state of the world to the player. Obviously, if you look at the Pong game, right? So very simple. The two pedal, right? Here's the score, right? The score, the two pedal, the net, and the ball, right? So that's it. And right, and then here's the one of the Mario games, right? And Quake, the very first 3D games, real-time 3D games, right? First-person shooter. And then, this is one of the Unreal Tournament screens. So you look at, wow, there's a big difference, right? From this, all the way to here. But at the very basic level, what you're dealing with, the basic element of a computer graphic, it's just one tiny pixel, a little square, right? That on the screen that you can change the color. You can change the color, that's it. That's really the basic element. All this thing started down by just coloring. So obviously this one, you can easily see that, oh, I color some of the white pixel white, right? And then some of the other, the backgrounds black. But even this one is the same thing. So we look at, let's look at, this Quake, right? Say, oh, that looks like a 3D game. But if you look closely, they're pixels, right? So they're pixels. At the time where Quake was first released, that the resolution obviously is not very high, right? So not very high, and the machine is not very high, so they're very pixelated, right? So they're probably, 680 by 4, something, by yeah. So then you can actually see, if you zoom in, you can see that this monsters and the things are quite pixelated, right? Even the firing, right? Now, if you go to the next, the real tournament, right? So now the graphics are much higher. Much better, right? So you can't really see the pixels anymore. What? Hello? So you can't really see the pixel anymore. But they are still, in fact, realized by just changing the color of the pixel. So you say, well, how do I do that? There will be so many pixels to do, right? How can you manage that? You can imagine how you manage that by doing the ping pong game, right? But how do you manage something like that? So as graphic becoming more powerful and more complex, and the resolution of the screen becoming higher and higher resolution, now you have 4K, you cannot just do it by pixel anymore, right? So you rely on high level libraries. So you guys probably heard of OpenGL and D3D. So those are the two different libraries mainly used by and then game engines, right? So game engine allows you now, you can just specify a character. It takes care of all the rendering by itself, right? So you don't have to worry, oh, I need to change this pixel. I need to change, then just imagine that'll be, you take a long time to make a game. So that's, really what, so there's a lot. In fact, a lot of very interesting algorithm in computer science are developed because of computer graphics. I know some of you are taking USICO classes. So if you look at, obviously, USICO is all about algorithm, but it turns out that many of the very interesting algorithms, particularly geometric algorithms, are all invented because they're needed to make computer graphic, to make it run faster. Okay, so that's the second thing, computer graphics. Right? And the third, user interaction. So that's how the user interact with the virtual world, right? So obviously in a physical game, well, you boxing or you play ping pong, well, you hold the paddles to do it. But in a video game, you need to interact with the thing that inside the screen. So how do you do that? So obviously, you guys are familiar with game controllers, so that's one way, right? Mouse and keyboards, right? So for PC games, the controller mostly for console games. But also you can have all kind of device. So obviously Guitar Hero being a very popular game, it's just a guitar, right? So, you know, there are buttons on the guitar, and that's another way to do it. And finally, some of you probably, you know, heard of this or use this, right? Camera. In fact, you know, with the computer getting faster and faster and computer vision getting better and better, using camera may be a very natural way for you to interact with the game, right? Much more open or much more flexible than, you know, because a game controller or the keyboard and mouse, right? There's only so many keys, right? And say, oh, you know, obviously some of you use, A for turning left and W going forward. Well, it's not so natural. But what if you can just use gesture, right? So that's what Connect was. When Xbox launched Connect, it's a way that you can naturally, using your own body motion to control the game or using camera. So that's all the different way to, but then obviously then the game need to somehow monitor, get those input, right? From the keyboard and from the controller, right? So that's another third part of the game. The game must, you know, look at these devices and then map what you put in the controller, right, the keyboard, into the appropriate action, right, in the game. And finally, but this is probably the most important part and most interesting part of games, is the game AI. So why do we need game AI, right? Or what is game AI? Can some of you tell me?
Artificial intelligence.
Yeah, so AI stands for artificial intelligence.
Like,
so how does artificial intelligence use in a game?
So like there's like another person who's not really real, but he's still in the game and he plays it.
Mm-hmm.
So.
Yeah, so the NPC, right, the name-playing characters. So in order for the game, like I said, you know, when you look at the definition, if a game has no challenges, has no opponent, it's not going to be a very fun game, right? So in fact, and in game, most game has NPCs, right? The non-playing characters. And obviously on online game, you can play with, like, you know, Fortnite, we can play with another player, which is your opponents. But many games, you have NPC, which are driven by AI. And how interesting your game AIs are would determine how much fun, right, your games are. So just let's look at one very simple game, right? So the design of the AI becoming very critical. And in fact, you know, it because of game industry, a lot of very interesting algorithms are developed, you know, around game AI. And then they're also, very interesting enough, a lot of very powerful algorithms are used in game AI. Some of you may have heard of this algorithm called A*, right? So it's actually invented for robotics, A*. A* is one of the most used algorithm in game, right, for finding path. There's a joke saying that if every time someone used game A*, you get a penny. So A* was invented by among other, one of the faculty at Stanford, Newsom. So if every time someone uses A*, he get a penny, he'll be a billionaire because so many people are using A*. But we look at something simpler. Let's just look at, you know, very popular game, and hopefully you guys have played it, even though it's not the modern game, Pac-Man. Right? So what are the enemies in Pac-Man?
The ghosts.
The ghosts. So do you guys happen to know what the name of the ghosts are?
I know one's name is Pinky.
Okay, one of them Pinky.
Oh, and then like, wasn't there one Blinky? Yeah.
Yeah, so there's Glide, the Blinky, Pinky, and Inky. So there are 4 ghosts. And do you actually know, are the ghosts just kind of moving randomly, or they actually are smart?
They're a little bit smart, I think.
Yeah, they're a little bit smart.
Like, I think when you get close to them, they follow you.
Yeah. So, but do you actually figure out, do you actually know, okay, so there are 4, right? So you say, okay, are the 4 ghosts behave the same, or are they all have their own personalities?
They have names and colors. But...
Yeah, so they actually all have their own personalities. So, so Blinky is also called the pursuer or the chaser. So he, you know, or he or she chase. So basically, you know, knowing where Pac-Man is, let's just call him she. Right? She just go after Pac-Man. Right? So that's a behavior. Now, on the other hand, Pinky it's called speed, or also the Japanese translation called ambusher. So it's a little smarter. Instead of just directly chasing Pac-Man, he actually go in front of Pac-Man where Pac-Man is going ahead of Pac-Man. So because you figure out, okay, it takes a little time to get to you, right? So if I get to you, you already have moved. So why don't I just go to block you somehow? That's why the name ambush, right? So we kind of ambush somebody. Now Enki is also known as bashful. So his target is not just Pac-Man. So they decide to combine Pac-Man and Blinky's position to determine where the target for Enki. So Enki actually go to where, if you draw a line between these two, goes there. So I think the idea is that, I'm just guessing, right? The idea is that, if you're chasing by Blinky, so you probably, would go forward, right? And then, so that kind of roughly projecting kind of where you go, right? And you go after that. So, but, that might be a rationale, but maybe not. And then finally, Clyde, it's called Pookie, but it's, you kind of have a very strange, it looks like, he's drunk. So it's called pretend ignorance. So Clyde kind of switched between two modes. When he's far away from Pac-Man, she would go toward Pac-Man. When she's too close, within 8 units, she will go away. So that's kind of the behavior, right? So, obviously, I assume there's a lot of thought put into designing those characters, not only because at the end you combine them, right, to make this game interesting, fun, and because you have to worry about, in fact, when you play this game, if all the enemies behave the same, then it actually might be easier, right, to do. But they're all slightly different. So just like in the real world, where you have opponents, even in a football field, right, some people run faster, some people are, the blocker that blocks you, so you need to kind of deal with. So in this case, what seems to be a very simple Pac-Man game actually have quite interesting behavior for all the different characters. And there's just one mode, chase mode. But Pac-Man also has 2 other modes called scatter mode. So scatter mode is really to give a player a breather, right? So because you keep chasing it, that the player will get so intense that you probably give up. So the scatter mode, all the ghosts will go back to their home right at the corner. So give the player some chance to just move around. And then there's also the frighten mode, is when the Pac-Man eat one of the special palette, and then it turns them blue, and then you can eat, and then you can go eat them, right? So, and then they're kind of somewhat frozen. So now, the design of this mode, it actually puts a really interesting way for you to design the game level, right? So every level, you just combine different, different chase time and scatter time and so on. So to make the level, increasingly more difficult. Obviously, as the level gets harder, you want to have more time chase, right? Less time scatter, right? So if you look at in level 1, so they, scatter for 7 seconds and then chase for 20 seconds, and then scatter again and chase again. Eventually, just only chase after. So that's how actually our game levels are designed. Once you have the ghost behavior, you can literally just kind of lay out a table to design each level, right? So we're going to talk a little bit when we talk about game design. How do you design level that's interesting, right? Progressively. Okay, so that's really the 4 component, right? Simulation, graphic, user input, and game AI. So obviously, we're going to talk about how to make games, learn how to make games. So the game class I teach actually use PyGames, and some of you may have heard of it, or how many of you actually used PyGame before?
I have.
Okay, so I'm going to tell you a little bit what PyGame is, very briefly, and then why do we use PyGames? So what is PyGame? Many of you probably have used Python Turtle, right? And in fact, it's a very, very fun way and intuitive way to learn programming using PyTurtle draw. So you draw a bunch of really interesting things. So PyGame is also a library, right? It's a set, it's basically a set of modules that work with Python, but designed specifically for using for making games. So you can think of them. It's like you might call it a game engine, right? But it's really more a module that you can help you simplify a lot of things. It kind of does a lot of things for you. For example, you don't have to draw pixel by pixel to draw a circle, right? You can just draw a circle. You can actually blip a graphic onto the screen, right? And then move all of them rather than try and figure out each pixel how it works, right? So it's really about, it's a set of modules that help you make game. So why do we use Pygame, right? So number one, there's many different way to make games. It's quite flexible, so you can actually make, because it's very low level, right? So you cannot use it to make 3D games. It'll be very tough, mostly for making 2D games. But you can almost make any kind of 2D games, right? So so this is like a platformer, a space shooter. This is one of the very interesting puzzle games called Sokoban. I don't know how many of you guys are familiar with that. A very, very fun game to design. You can make any game, pretty much. Quite easy to learn, right? Assuming you have some background in Python, it's actually quite easy to learn how to use Pygames. And obviously you use Python. So a lot of you obviously realizing that Python is a very important language, and many of you want to learn Python. So this will be two things: to learn more Python, and then put what you learn in Python to use, right? And finally, this is actually important. Pygame actually are compatible with a lot of different graphic and sound formats, right? Like MP3, JPEG, or PNG. So a lot of those graphics are available. You can buy them, with little money. It's like $10, $5, $2. You can buy some very nice graphic. A lot of them are free. So, and actually, I can show you some of the things that I did. That just, you can download graphic for free. Obviously, you can resell them. So it's very easy to get graphic or sound format to work with it. Right? So those are good reasons. So also it has a pretty good online support, right? So the wiki, you have a lot of document, and then also a community, you can share the game you make. So in fact, you can go on Pygame and see a lot of games that people make and update, and they share them. So it's kind of a fun way to share what you've created. So finally, the last thing I want to talk a little bit about is why do you, or why, I guess either to help you answer this question or help your parent to answer this question. So somewhere you say, okay, so hopefully by now you realize that making game is not, it's actually quite hard, right? And it's actually involve a lot of computer science. But I just want to give you a little bit more concretely what are the things that you would learn and actually learn to make games. So in most curriculum, and then obviously the one I teach, it mostly is project-based, right? So we actually, it's centered around project. So every class about, we're making a portion of a game, right? So we'll make different games from simpler ones to more difficult ones. But we're focusing on learning the fundamentals, right, of computer science. So in two different ways. One is more about the algorithm involved, right? So if you remember the thing that we have to, the component of the game, right? Graphics. So computer graphics has a lot of very interesting algorithms, from how to draw things, or how to draw things more efficiently. So there's a lot of very interesting algorithms. Simulation. So obviously, you need to simulate the world. So in simulating war, again, there's a lot of very interesting problems to solve with algorithms. So, physics, collision. I'm going to just talk to you, give you a very brief example about collision detection, so we can actually see how much is involved in something that looks very, very trivial, right? Or simple to you. Game AI, we always found that, right? And also, so the other part of curriculum is we'll be touching on a set of new programming paradigms, which is particularly two things. One is called event-based programming, right? So game, as opposed to other thing that you do in like a APCS class or in musical, is live, right? So things are happening in real time. So you can't really just do it sequentially, right? Step by step. So this is, as computer being used in more and more application, this event-based or asynchronous programming becoming more and important concept. So game is a great way to expose that, because game by nature is a real-time system. So you need to deal with events. And second is about object-oriented programming. So in the third, in later of the curriculum, we started, as to building more and more complex game, which is you have, different enemies, different weapons or different objects. You then, getting everything just simple, without using object-oriented programming becoming difficult. and game is a great way to expose why do you need to do object-oriented programming, and how do you do that, because it helps you visualize. So again, I'll just give you a very quick example to just highlight a little bit, how does what seems to be rather simple things in a game actually involving quite a bit of algorithm. So collision is one of the things that use a lot. In most games, you need to do some kind of collision, right? So I guess you few example. So this is like a space shooter. Why do you need to do in the collisions? You need to make sure that your plane doesn't collide with other plane, right? When they collide, obviously something wrong. Or the bullet actually hits those planes, right? And then when it hits, there's an explosion, right? This is a runner. So runner, when you run, obviously, you don't want to go into those spinning saw, right? So you need to jump. So obviously you need to detect that you run into something, then you die, right? And obviously, good reason why you do a collision for a racing game. So seldom there's a game that you don't involve collision detection. And there's, obviously, collision detection, you look say, oh, of course, two things collide. Well, it's actually quite difficult to compute, quite difficult in general. So I'll just give you one very example. Hopefully you guys can work it out at home to see. So, and there's sometimes to speed it up, you simplify things. So that's normally what we do, right? So rather than trying to figure out what this character, all the detail, how it collides with this spinning saw, you can approximate them. So we call them bounding box, bounding sphere, or bounding rectangle. So you can actually just simplify them. But obviously when you make it into simplified, very simple, like a circle, then it's not very accurate, right? So you're trading off the accuracy with efficiency, because colliding a sphere with a sphere is very easy to do, right? But even a rectangle and a sphere is not so easy. But I also want to show you, so then how do you do that? Like a very simple problem of just checking, you approximate this guy by a rectangle and see if it actually collides with the saw, right? So say, oh, that's pretty straightforward. Well, I want you to think about, right? How do you check? So I'm going to give you, so I actually leave you this as an exercise. How do you figure out how to find a bounding box, a rectangle, even aligned with X and Y? So this is not even rotated, right? How does it collide with the circle, the saw? So if you want to make this game, well, you kind of have to figure that out, because otherwise, this guy would fall into a saw and this looks strange, right? So so it turns out that you work out an algorithm is that you want to find the closest point of this rectangle that's closest to the center circle. That's what you want to find, right? And then how do you do that? Well, you actually have to kind of figure out all the different cases, right? You kind of figure out different cases, where the circle relative to the box, or the box related to the circle, but you need to figure that out. And after you do that, you actually figure out all the cases. And then you actually can generalize to a solution, right? So I'll just leave this. So I want you, if you think, right, just go home and think about that. So again, this is just like for object-oriented programming. How does that relate to, well, you have the hero, right? So a hero is an object, right? And then you need to figure out, everything you need to do with a hero. You can start with something simple, the speed and so on. As you go, you need to draw it, and hero might get hit and all those stuff. So since we're kind of running out of short time, I'm just quickly going through this. And it's very interesting about event-based programming. This is a new paradigm, right? So in games, just like in real life, you need to kind of monitor multiple things at the same time. You cannot just worry about one thing, right? So for example, in the shooter game that we just looked at, you need to worry about, obviously, the game need to worry about, okay, the user are trying to control the plane, right? So you have keyboard input, right? At the same time, you're shooting, right? Shooting things out. But then the bullet that shoots out need to make sure, if you hit the plane, then the plane will explode. So how do you worry about taking care of all these different things at the same time? And this is, the thing that we, around event-based programming, right? And all this can also happen asynchronously. It's not that, oh, after you put the L and then, you do that and do that. No, because it can happen anytime. The bullet can, hit the plane anytime, right? So it's not like after you do something, obviously, right? And then you can hit the button to fire or to move left and right anytime. So this is actually a big part about event-based programming that's critical in game, but also becoming a very important part for the modern computer science, as computer science being used more and more in real life, because life is event based, right? So those are things that we learn. And so now just going through very quickly about like what do you get from learning games, right? Or why do we propose? And obviously there are many game classes, right? I think obviously one thing is that, it's motivating. Kids like to play games. Many kids like to play games, and it would be a good way to say, oh, I can, at least learn how games I like to play, how they make, or just make something games, and understand how game making in general. So that's a really a way to motivate that. But actually, most importantly, I think this is the part that I want to emphasize on. Games are visual. Right? Games are visual. You see things, right? So whatever you do in programming, is because you want to see something, right? So this visual aspect of it makes it really helpful for a kid to learn abstract concept. So I want to just give you an example of that in a second, right? So the second. And third is really to help kid to learn solve problem algorithmically, right? So in a game, every day when you program a game, you're facing a problem, right? Oh, how do I fire the bullet? How do I check the bullet hitting a plane? How do I delete a plane once it's got to explode, right? So all those are problems, right? So, and you need to solve it by programming. So really, help the kid to learn how to solve problems algorithmically, right? And then, in fact, games are simulation, as we saw. I mean, that's the first thing we say, simulation. And in fact, just has a good grasp of computer simulation is very critical for computer science, because many computer science problems, even some of you are taking user codes, right, are simulation problem. So a simulation problem. And finally, so those are main things. And then, so I just want to emphasize a couple of things about game and visualization. So if you have learned programming, you obviously, you know that you need to learn all this, right? Variable, list, iteration, loops, nested loops, conditional, all this thing. And usually pretty dry, something like this. You go through a list, you print something out, right? And you can learn it this way. So there's nothing wrong with that. But it's quite, abstract, right? So it's also, you can say quite dry. Now, but when we do game, we do the same thing. For example, this is the Space Invader game that I was writing, right? So obviously, when you do a Space Invader, you need to make spaceship, right? The enemy, right? The alien. Well, you need to put one, right? So that's a variable, you put one. Well, then you say, okay, how do I put more? Right? How do I put a row? Well, you just, you iterate through, right? For I, things, and you can actually see them, and you put a gap in between them and how long I made them, you can iterate. And you say, okay, how now, instead of putting one row, I need to put multiple row. Well, then you need to, in each row, right? You also, for each of the 12 positions, you need to put multiple, for multiple spaceship, right? Multiple, so for each row, you have, for each column, you have multiple rows, right? So then you put the row inside here. So that's a nested loop, and that's how you get the, the alien. So you can, everything you do in program, you actually immediately see. If you did something wrong, I tell you, you immediately see something wrong here, right? It's not what you want. So the feedback's very visual, right? And it's also gratifying, because then you see exactly, what you program. So I think that's, and then also as you start seeing the process is becoming more, well, number one, more satisfying, because you now start seeing things moving, but also it actually helps you to understand this whole process, right? Instead of just, so variable, static, and simulation. So let's look at, let me just give you a quick example. So, you guys always, I don't know how many of you guys wonder, how do you, obviously in a game, right? So the character runs. How, normally, right? So if you actually, I download this list of a run cycle, right? For Little Pumpkin Boy for free online. So now how do you make this Pumpkin Boy run, right? So in a side scroller, how do you make them run? How do you make him run? Any idea? How would you make this Pumpkin Boy, right? So you're giving, you have eight frames, right, of the different poses, right? How do you make the boy run?
You animate it, so you like.
But yeah, how do you animate them?
And then, well, I don't know, but then you have to also move everything else, like have everything else move the other direction, so it looks like the guy's moving forward.
Yeah, oh, you're very good. So obviously, first of all, you want to take advantage of this frame, right? So to make it. So how do you do that? So actually, this related to, do you guys heard of this? The first time that they actually animated a horse running, right? Because so basically, you look through a slit, right? But through the slit, you see a horse, right? A frame, and then as you spin this thing, you actually are quickly seeing, you're playing the different frames very quickly, right? You're playing the frame very different, very quickly, and that makes it the horse running. So it's exactly the same idea, right? So that we want to do that in program. So let me just see if I can quickly show you that. Let me see. I need to share this. Okay. So let me see the space animation. Okay. Right. Okay. So now, I just make him run, right? So, obviously you say, oh, so I'm just cycling through all the frames, right? All the frames. So you say, oh, he's going a little fast, right? So now can we make him go a little slower, right? So now how do I make it go a little slower? I don't want every frame, I don't want him to go to change a pose. I was like, okay, I want to go every 4 frames I want to change. So you can actually divide by 4. And module, you have 8 frames. So I load the frames in, right? So this is basically what I do, right? I load the frame of the pumpkin boy, right? The 8 frames. And then in the loop, I just play them, right? So now now it would go slower. Right? So it runs, right? Can you guys see the screen?
Yeah.
Okay.
Yes.
So now, obviously, that doesn't work, right? He should run. He should go forward, right? So now we can, make him go forward, right? So again, so everything. So I want the boy's X to go, as you go forward, right? So, and I just want to go through this quick experience quickly so that you can see how, with game programming, the nice thing is that everything you do, it maps into a visual, right? So now you see, oh, so now he goes, right? He runs. Now there's a little bit of a problem. Like one of the students was saying, well, then he runs off the screen. Well, that's not good, right? So how do we fix that problem? How do we fix that so that he doesn't run off screen?
By making him stay in the same place and the background moving in the opposite direction.
Exactly. So so instead of having him move, right? So you can focus on him, right? And then you can move the background backward, right? So let me see if I have see, I have one of those things. So you can actually make the screen going backward and have it go in the steady in the things animation. Let's see if I have that. It's a dying character. So let me find, hold on a second, let me just find it. So, but that's exactly the idea. So you can have the screen going backward, right? And then the character just staying in the middle, right? And then looks like then he's running forward, and then the background stay in the back. Just that then he will never run outside. So let me, so I just want to finish this up before I, so I can find that and show it to you at the end. So now, so the other interesting thing about learning how to program is the algorithm involved. So you guys have played this Candy Crush, right? Fun game. And you look at this game and say, oh, this is a very simple game. So it shouldn't be hard. But so you notice this game, right? When you have 3 or multiple things, candy of the same color, they annihilate, right? They kind of, they all, disappear, and then all the candy will come down. So how do you make that happen? How do you make the candy, right? How do you, in a game that can detect all the candy, right, that are next to each other with the same color, and then you make them disappear? So it turns out, this is what has to go with a really well-known algorithm called the flood field algorithm. So some of you Again, if you do competition, you heard of that. So flood field algorithm is basically saying, okay, I want to say, let's say all the gray areas. I want to find all the connected gray area and change them into black or change them into basically empty, right? So how do you do that? I can just go find any particular one, right? So any one of these red candy, I go to look at the 4 neighbors to see if they're red. If they're not red, I stop. If they're red, I recursively, right? So to look, get the neighbors of the red one, except I don't go back to where I was, right? So it turns out, with this, this is the algorithm, right? Using recursion. So if you look at a very simple game, like Candy Crush, but behind it, there's some actually very interesting algorithm involved. It turns out there's another game. So this is a musical problem, right? A silver, right? So pretty hard, problem 3 musical. There's a game, the title called Muyu Muyu. It actually came from a very popular Japanese name called Puyo Puyo, which is kind of, this is a game that inspired, I think, the Candy Crush and some other game. It's similar to Tetris, except it's the ball. So this problem is exactly, this game, right? And how this game works. So as you can see that, a simple game, underlying it actually has a very sophisticated algorithm involved. And as we develop game, we're trying to figure out how to solve those problems, right? So same thing with Pac-Man. How does Pac-Man find the path, right? There's very interesting algorithm that can do that. With local method, or you can do the path finding. So, so that's kind of, there's, like I said, I want to back up a little bit. So really for this, what we learn in game programming, 2 things. A lot about algorithm, right? So how do you, because we need to solve problems, right? So in solving problem, you develop algorithm. So some of the things that looks very trivial in a game, but actually underlying it has quite deep and quite sophisticated algorithm involved. The second is really in learning game, it helps you visualize, right? Because everything you do, it comes out in a picture, right? In a moving picture. So if you do it right, well, it will look right. If you do it wrong, it will look wrong, right? So the feedback is very direct, right? And so finally, so let's just, before I open up for questions, see if you guys have any questions. So I just want to, so what is this class for? So it's really for students who are interested in learning, making games, but really more importantly, you're interested in the fundamentals of how the games are made, right? So you want to understand the basic algorithm involved, right? How do you do, properly event-based programming, right? How do you develop algorithm, right, for solving different type of problem, right? It depends on the game you make. So we're really taking the computer science approach to game making, but also since we're using Pygame, so students should have some basic programming background, right? So it's not, we're not talking about using Scratch, right? Making games. So it actually, you need to, as you can see, we actually program, but we don't really assume that you have, a lot of background, but you should have, exposed to programming. Preferably, you have done Python, right? You have learned how to program in Python before. You have taken the intro to Python class and so on. So you're familiar with Python and programming. But what this course is not for, right? So I want to just make sure that if you already have done Pygame programming before, you have made Pygame, well, this may be a little easy for you, right? Because I don't want to assume everybody has done Pygame before. So I'm going to start with something rather basic. So if you've already done a lot of game programming, this may not be for you. Also, we'll not talk much about game design, although game design is a very interesting topic. So we'll make mostly classic games, right? Game that's been designed. So we'll follow the game mechanics of, well-known game, right? A space shooter, platformer. So there's things that and then obviously I encourage you to add your own creativity to it, right? That's more than, that's obviously more than okay. But we're not focused on talking about game design, right? So it's not about a game design class. We're not talking about how to make mods in Minecraft either, right? So, and there are many classes that teach you how to make mods in Minecraft. So it's not that, because I really want to teach you how do you make a game from the most basic component, right? The fundamentals of it. And also we're not using any particular game tool, right? So like Unity or Godot, none of those, right? So we're just using Pygame, right? You can think of them as a game engine, but it's really more a library that you input in, right? So just, kind of just want to be clear. So finally, this is a quote, right? So, I hope, you by at least listening to this, now you get a little better understanding of how games make, and hopefully, if you don't want to learn to make game, you will at least, when you play game, I hope you appreciate more how games are made, right? All the, very simple thing, like Candy Crush. Well, how those candy actually annihilate, underlying it, actually some very interesting algorithm. So it's not, something looks trivial, but it actually turns out to be a lot of engineering work behind it. So at least you appreciate that. But also, they might motivate you, right, to learn, not necessarily make game, but at least you start learning computer science, so that at one point you learn how to make games. So that's it. So I will open up for you guys have any questions?
Did Barack Obama actually say that?
Well, I don't know what exactly he said, but he at one point, right? So, there's the quote, and I think he definitely instituted this 1 hour coding, right? So everybody, he suggests that everybody in the in school should spend at least learn one. Obviously, you can't really learn much 1 hour, but you should you would expose to what coding is, right? And I know some of you guys probably have programmed many more hours than 1 hour. Any questions? Let me just stop sharing.
So this course that you have, you just talked about, how many students do you normally take in a class?
So since this is a project based, right? So I would say normally less than 10 students. And then it will be in class, we normally talk about what we do, and then they all sign a project. And then I would have, if the students more than get to 10, then I will have an office hour once a week to help them, right? Because some of them always have questions. But most of the time, so for the AI class, I taught there was 9 students last semester. So I would say between 6 and 10. I would start a class if there's more than 6 students, and then if there's more than 10 students, then limited to 10.
Okay, thanks.
So have you any of you the student has made games before? Have any of you make any games in Scratch? And I know that's one of the interesting things that some of the students taking Scratch class would do that. Or have you done mods in Minecraft? No.
Okay, Dr. Zhu?
Yes, I can't. It's kind of. Can you speak up a little bit?
Yeah, Dr. Zhu. So I'm asking for my son. So for the class, how long is each class?
At this point, we're thinking about 1.5 hours each class, and then I would break the. So there, I would break into 3 sessions, right? So every session there's 10 classes, and the focus would be so the first 10 classes right now in the winter, right? So in the winter 10 classes, then we'll do some of the simpler games, right? And then, but we'll do a complete game, so the whole loop, right? So you make the game from beginning to end. And the second session, which would be in spring, will focus a lot more on AI, how do you make interesting AI for the game. And the third session, which at this point we're planning for the summer, would be focused on more the level design. How do you design the level and make them rather than one level, how do you be more challenging, right? So each session has 10 class. Each class, at this point I'm planning for 1.5 hours. And then there will be a project. So there'll be like 2 or 3 games of project. The project usually would be over multiple class, right? So like 2 or 3 class, or maybe even 4 class. So at this point, I'm planning to make 2 games in the first sessions, right? So that it would, but they're project based.
Okay. So what is the format of each class? So like, for example, how much time per class might be spent on you giving a presentation or more of a lecture style of instruction, teach kids how to do things versus checking on each kid's work.
Yeah, so I would spend the way that it's I think it runs in the past. I would spend for 1.5 hours. I probably spend about an hour on materials, right? So how we do things. I expect them to do most of the stuff at home, and then with the office hour to help them, right? So if they need to have questions answered, but then for the first half an hour, every class I would normally have students to present what they made, right? Or they might have a questions from the last assignment. So I think this part is very useful, right? So so they can ask a question, say, oh, I got stuck, and they can do that for the first half an hour, or they can just present what they did. It's a I find out for even for the musical class I taught, the student normally come up with quite unique solutions, right, to problems, and having them share it and having other students to hear it is actually beneficial both ways. So the class the first half an hour would be more students sharing, or they might ask questions, and then the 1 hour would be the material, right, that we covered. Maybe the last 15 minutes of that would be discussing the assignment for the week, and then they would do it. And then they would, if they have questions, they come to office hour, and then otherwise they will present their progress the next week.
I see. So for the first half an hour, students will take turn to present what they have got.
Yeah, so they would, so it depends on them. So I would probably normally pick 2 or 3 students, or a student who have questions, right? So basically, about 5 to 10 minutes, 5 minutes per student to present what they have done, right? Or the challenge they have met. I mean, it could be either, right?
Okay, share with the whole class. Basically.
Yeah, exactly. It's what I found is that, again, for different classes I taught this same format, is that being able to articulate, right? A lot of times they did it, but they didn't really know, they can't really explain why they did it. So having that, and that's one thing. Second thing is that having, this is particularly important for programming. And in gaming, quite creative, right? So a lot of students having they develop different approach. Some approach I didn't even think of myself, right? And having students see each other's way of thinking, right, is very beneficial. And that's something that you cannot get by just listening to one teacher, because if I teach, I will teach it one way, right? But very interesting. When you have, anytime when you have 4 or 5 students, normally 1 or 2 of them will have some very unique solutions.
I see. And how do you plan to accommodate students that may have different capabilities?
Yeah, so that's a little challenging. So I'm trying to, that's why, at the end, I put down, so if, you're trying to make the class more or less the same, right? So I don't want to have any student who actually make Pi games before. I mean, they'll be find it boring. But I don't want to have any student who have never programmed before, right? So I'm trying to, that, but even within that gap, there's still, students make, well, obviously they make progress differently. So the 2 things. So in projects, that's a nice thing about games, right? I want to make sure that they would get the basic game, the basic part done, right? It's designed for the kind of the for everyone, right? But also in game, there's also so much more you can do. So if you're making progress faster than other students, there's always a challenge, right? That you can do on your own, and you can share that. And so that's really the way that the curriculum design. And then also students who have problem, normally they would come to for this classes with more than a few students, right? I normally have an office hour every week, and they just come and ask questions, right? So the students who are having more trouble, they come more into the office hour than students who are no trouble.
And the class is once a week?
Yeah, the class is once a week.
Okay, and then office hour is once a week?
Yeah, office hour once a week. So normally it's like 2 or 3 days after the class, right? So they spend some time working on the problem, and then they would come and say, oh, I have a questions.
Okay, thank you.
Yep, sure. Any question from anybody else?
if we did a lot of like scratch programming, do you think that will help in terms of game design, or it doesn't make any difference?
Well, if you've done a lot of Scratch, the concept of game, right? In fact, Scratch is very interesting. Scratch is by itself multi-threaded and event-driven, right? So what I call event-based. So it's kind of quite natural to him that say, oh, things happen, right? So you've done a lot of making games in Scratch. He's definitely familiar with, the game making part, right? Or the design, right? But then the challenge that, he needs to somehow get to start programming in a language rather than Scratch.
Rather than Scratch.
Yeah, so so Python is obviously there's debate, but now mostly people agree to that. So Python is probably that's the reason why we decided to choose Pygame. So Python is probably the best first language you learn, right? If you're after Scratch, you want to learn a language. Obviously, you can pick Java. You can pick C++. I would say many people ask me, right? So Python is probably one of the most friendly. Obviously, you might pick Java because APCS is in Java. But if you're independent of that, you say I want to pick a language to learn. Python is probably the right language to start.
When will the class start?
It will be probably starting the second or third week of January because. So you'll be, because we'll have 10 classes until the end of March. So I'll probably pick 10 weeks, probably second or the third week. I haven't decided whether it will be a weekday or weekend. I will send out email after this talk to just get some feedback if you're interested in, maybe some time slot that works. So I haven't really thought about, so I'm gonna send an email out so that people who are interested in, they can put in some feedback as to. And also I get a sense of like the level of the students too, right? So.
And you mentioned 10 weeks, so you're planning to follow on with another one in spring?
Yeah, so this is like the AI class I taught, right, on teaching. So I broke the class into 3 sessions. So for the AI was was fall, winter, and spring. And for this one would be winter, spring, and summer, I guess. So each would be 10 weeks. And then the focus would be increment, getting harder and harder. There'll be different focus. Like I said, the first 10 weeks about, it's really about the graphic, the simulation. The second week is about, the AI, right? The third week is more about, tying together with the UIs and with the level designs and so on. So so you can think of them as sequels of 3 sessions. Does that answer your question?
Yeah, it does.
Okay.
And in terms of collaborative work between students, is it individual work or collaborative? And if they're collaborating, how do they actually collaborate on?
Yeah, I mean, so they can work collaboratively, right? So, but in fact, before when we have in class, right, in the location class, it's easier. Now, obviously, they can still collaborate, but at least for the first. I'm thinking maybe for the last session, or maybe the final project in the second session, we can do they can do a group project, right? So someone is better in in AI, someone better in the simulation part. They can probably, but would be a group project, right? The student can share, but I just need to figure out how easy the logistic is. But at this point, at least for the first session, my plan is just to have they have them work individually. I mean, obviously they can share and talk and discuss, during the class or after class, right? But the project would not be collaborative.
Are there particular grade levels that you expect students to come from?
Say that again. The particular level.
The grade level, like the school grade level. I guess the kind of.
Oh, you mean like what grade are they at this point?
Yes.
Not really, right? So, but I would say, in general, as a guideline, I don't really suggest people start programming in Python when they're second grade, right? So, I mean, people do that. I would say, so kind of ideally, right, for people would be 5th grade, if they have done quite a bit of work in Python, 4th grade, and then all the way to, well, if you're still interested in doing this in high school or have the time, that's fine too, right? So I think kind of ideally would be like 6th, 7th grade, 5th to 8th, 5th to 7th. But it's really more about, because, for programming, right, some students, they started when they're 3rd grade. Some people started in the 2nd grade, right? It's really more about their background than the grade. Now, for this is slightly, but obviously, as we start talking more about the algorithm, students at higher grade, I think they would probably have a faster grasp what that is than the younger student. But like I said, I make the project so that the simple level of the project, you can solve it without much of the. It doesn't require very sophisticated algorithm, right? So just basic. So it's more the background of the students. Have they learned Python before? Have they done programming before?
So besides the office hour, would you have like a Slack channel for students to ask you questions or collaborate?
Yeah, so they all have, a lot of students, they send me emails, right? So I've been, some of you may probably know, I've been teaching musical training, right? So they all, when they have questions, they always send me emails.
Email is the main kind of communication channel.
Yeah, so that's probably, and then if I cannot explain it in email, then we can just schedule a Zoom call, right? So, but most of the time, it can be done by email. Right? So there were questions.
Okay.
Any question from the other parents or any students have any questions? Because you have a lot of parents have questions. Okay, so I was reach out to you by email or the WeChat, I guess group, and then if you guys, or whether the students or the parents have more questions, you can always just send me emails or send me a WeChat messages. Okay. Well, thank you guys, and happy holidays.
Thank you.
Thank you so much, Dr.
Yeah, thank you.
Thank you. Thank you so much.
Bye bye.
Bye bye.
Sorry.